recording on? Okay. So welcome to the lecture of Piotr Gwiazda. Piotr is a full professor at the Institute of Mathematics of Polish Academy of Sciences and at the University of Warsaw. I met Piotr around 2010. And then he was the head of an international PhD program under the title Mathematical Methods in Natural Sciences, which ran from 2009 to 2015 and involved 9 institutions, some in Poland, some abroad. And this was a program devoted to PhD, to the training of PhD students, and funded by Foundation for Polish Sciences. And I was appointed by this foundation to observe the program and write reports. And I remember that I wrote at least 2 of them, and both were highly positive. And I was really impressed then.
In fact, if you were anonymous.
No, I was not, because there were some interviews. I was not anonymous. No. If I were anonymous, I would not tell now. No. I remember that I observed lectures by students. For instance, Ewelina Zatorska, who spoke on Monday, she was one of the PhD students in this program. And it was very difficult to obtain this program because someone needed applications. So this was for applied PhD students, but Piotr was clever to write a good proposal, and he got it, and I was really impressed. And I think, from the perspective, I think that this program has a profound impact on Polish community of PDS people. And then I understood that Piotr is a community builder, and he's still like that. Yeah, and that I appreciate it very much. And this year he got a grant maestro of National Science Center, which is also a grant of kind of a big grant with money for PhD and postdocs. So it's like a continuation of all this involvement. And it's also very prestigious because a competition is between mathematicians, physicists, and engineers, and it's always for mathematicians too difficult to impress the jury. Okay, and a year ago, Piotr also, he got a position at the Interdisciplinary Center for Mathematical and Computer Modeling at the University of Warsaw. And it will be something about that in your talk, I guess. Okay, so the floor is yours, the Zoom is yours, please.
Thank you, Eva, first for invitation and also for very kind introduction to my person. I will say that this is something in fact, with these both projects, this is something what was important is that the both projects were evaluated by interdisciplinary panels, means both this in Foundation for Polish Science and also in National Science Center. The smaller grants are evaluated by the mathematician, by so-called ST1 panel, which is panel only built on the mathematician, and in fact the maestro grant is evaluated by full panel of ST, which means translating to English, this is a panel for technical and science, because in science, in English you have science and humanities. This is not completely consistent with Polish meaning. And then the panel is quite big, and what you need is to convince that the mathematics is, to get it, is important, is to convince people that the mathematics that you are doing is not important only for, proving some theorems, but it has some broader application to different science. And I think it was also quite important lesson to me, you know, that how to somehow to find something what is I think both from mathematical point of view is interesting because the interesting mathematics, but also is important for the from the level of the applications. And we were talking here about the ICM. In fact, this is not weather from the, this is our weather forecast. Maybe you are using this this service. You are quite young generation, then probably you are now using something different, like, for example, Onet, or you know, in Apple. This is Krakow. This is not Poznan. In fact, this is a slide from my interview with the Maestro panel from this area. As you see, it was 21:01 exactly, and it was prepared for this interview. And this is the, in fact, exactly what one of the activities, in fact, quite important activity of the ICM is just to do the weather forecast, to compute the weather forecast for this area. In fact, our weather forecast, this is only the part of the, we are not doing weather forecast for full Earth, but we are doing only for some area. We are doing for this area, which is important for Polish Navy, for Polish Army, and governmental institutions. And in fact, this is the area around Poland plus Baltic Sea, because Polish Navy is just on the Navy. Navy is on the Baltic Sea mostly. In the time that Poland was in Afghanistan, we were also conducting the computation for the Afghanistan and also Iraq, depending on time. This is project which is quite long time project. And you know, this is in fact, for this we have at Białęka quite big computer center, like 10,000 square meter of server spaces with some, you know, electric supply of really, this is a huge equipment. And but if you see, okay, there is a question, where is the mathematics in this? And in fact, the mathematics is simply that the computation are based on the generally on the Navier-Stokes equations, on the movement of the air due to the Navier-Stokes equation. Not like, you know, incompressible Navier-Stokes, but this is much more complex, but still. And in fact, this is what is behind. This is some important problem, which is behind. There is also, of course, there is also the question of, this is also the model of wave on the Baltic Sea, which is also the part of our model. And what is very important for this story on the theoretical side, this is there are some issue of numerical analysis of the stability of the numerical scheme which are used there. Also some questions close to so-called singular limits between different models, means how to pass from one rigorously and from one model to another one. But there is also very important issue which is not really well understood till now. And this is frequently used by this atmospheric model. This is the issue of data assimilation, means how to, for the forecast of the weather, how to use some additional information that you can get, for example, from some meteor radars, also from some meteor station. And the most important problem in the weather forecast is that for this type of the PDE which are hidden behind of the model, to conduct the computation, you need initial data. Means, in fact, you need to know the temperature, pressure, and the velocity of the air. Let us say at each point at the time of that you start your computation. And this is something what you cannot get. And there is some mathematical method close to this data assimilation, how to start the computation of the PDE, not having information exact information about the data. And this is based on some so-called method of determining mode, something between the PD, Fourier analysis, and really, you know, the people who are doing this somehow not completely understanding what is the background. But if you want to go in the background, this is really interesting topic for the analysts and to understand what are the limitations. There is a lot of mathematics which is behind. And in fact, I want to stop this topic. This is one of the topic of my Maestro grant, and pass to the some different topic. Another topic is the somehow closed, but not completely. This is the topic of machine learning, or some theoretical aspect which are behind of machine learning. Mostly as we have machine learning, the thinking is there is a black box, some model, you are teaching the model and getting some output. And this is what most of the people doing machine learning, they are testing some models with some situation. And what is typically people are doing this, that they are taking model, taking some data set to teach the model what should be the answer, and then they are testing in several conditions this model and saying, okay, now we are happy. The problem is that this approach is extremely dangerous, because in some condition the model is giving you proper answer and in some not. Everyone using ChatGPT know that the mostly, even the language models, mostly you are getting quite nice answers, and sometimes the chat is hallucinating and producing something what is completely nonsense. And if you lost the ability to control this, that's done. You cannot find what is the hallucination of chat and what is the correct answer. And this is in the machine learning, there is very important is the testing versus verification. And testing means that you test your model on several conditions and you are saying, I'm happy. I don't care what happens if the answer will be wrong and you know, will produce some troubles. And another is the situation that you find some rigorous method to get that the model is really answering almost correctly in all conditions. This is completely different. And for the first, in fact, you don't need mathematics. You need only the people who know how to, you know, the create algorithm, or even how to use some tools. And for the second part, definitively you need a lot of mathematics. And this is the problem. And I will in fact start not on the level of machine learning, because this is a more advanced, but I will start with something much simpler, which is also in machine learning. This is so-called sampling. A sampling is simply you have some big set and you want to take from this big set some smaller subset, which will be representative for this big set. And how to choose it? In my context, the sampling will be something else, but similar. In fact, you have some infinite set, means you have, for example, some distribution, and you want to represent this distribution by some empirical distribution, which is also the type of sampling. And in fact, I will most go in the sampling in the Bayesian context. In the Bayesian context, if you want this is in context of, because there are several contexts of these samplings. This is machine learning. It's much more complicated. Bayesian, I will say, is the simplest one to understand what is going on. And the first, probably from the probability theory, you remember the Bayes theorem. Fortunately, probably I don't remember, but you are mostly the student, that there is still the chance that you know in the probability theory, or even in the school, you have a bias theorem, and this is, you know, and the Bayesian approach means that you have some prior distribution, which is in fact some initial information. For example, you know that the range of the parameters should be in some interval. And then you have something what is called likelihood function. And based on this, which is in likelihood, you have your model, you want to get some posterior probability. And the posterior probability is, for example, answering you ask based on some measurements and the model, you ask what is, for example, the distance between the sun and Earth, or sun or Earth and moon. And then you want to get the answer, which is not exact, because this is mostly the, quite frequently, this is over-determined model. You cannot get really the exact answer, but you are getting as an answer some probability distribution. And this is, the model is, you know, because this is inverse problem, then the bias is on the head. And the model is, in fact, the simplest situation that you can, to be really concrete. The simplest situation is that you have a model, you have some parameters, some function m, which is just saying, okay, if x is something, then m of x is something. And you want to find somehow the best fit, and you are assuming that there is the simplest situation always is to assume that the error is a Gaussian type. And then assuming that probably even in the probability theory, you have the description of the Bayesian inverse approach, then I will not really spend so much time on that. And in this context, what you are getting, in fact, you are getting that the bias or the posterior distribution which you have is something, this is in the statistic, it means that this is proportional, means you know, in fact, your distribution up to the normalization constant. And the full game is in two. One is that you know what is the evaluation of your potential if you can evaluate this m of x, and in most models this is not that you have some algebraic expression for m of x, but m of x is, for example, the solution of some PDE or something like that, which you need really to compute on the computer. And then the story is that you have a form of you are looking for the probability which is proportional to this function with some given potential, however, given not in the sense of algebraic m of x function, but simply that it can be computed on the computer by some algorithm. Generally, this function can be computed, can be really, if, for example, you are applying this approach for some PDE models, the computation of this m of x can be quite costly, means that each step, if this is simply algebraic, it is very fast. But if the model is complicated, computation of this guy is costly and takes a lot of time of the computation. For example, for this, you are solving the PDE on some interval. It's complicated. And of course, there is, as you see, there is some interpretation of all these guys. Of course, here, this is simply this covariance with this given gamma. This is a posterior. That's fine, typical for the Bayesian approach. And typically, what people are doing, people start, as you see, around 1954, in fact earlier, because this is a paper from this year, sorry. And they start with the algorithm, which is called Metropolis Hastings algorithm. It's also very well known for the Bayesian statistics to be able to compute it. Typically, you are using some algorithm which is just saying, okay, what you are doing, you are staying somewhere, and you are making step, and then you are deciding to go back or stay in this new position and make the next step. This is the so-called acceptance rate in the Metropolis Hastings algorithm. And as you see for the application, because here is Journal of Chemical Physics, another one is Biometrica. This is for application, something what is really frequently used. What are the disadvantages of this? The disadvantages is that here what is behind is they are ergodic property of some Markov process. And if you want to create the empirical distribution based on this Markov steps of this Markov algorithm, then it takes quite long. The beginning is really useless, because this is coming somehow from different distribution than that you are searching this, because this Bayesian with this algorithm, what you can get is you can get this distribution, Bayesian distribution. This is important, is that you know the distribution up to the normalization constant, and then you are getting this is familiar to you or not? A little. Yes, for some, like for Łukasz, of course, yes, because he's working on this in his master thesis, but and even I think before okay, doesn't matter. And but this is this is one of the most popular algorithms used for this Bayesian inverse problem. But the disadvantages are that this is a quite slowly converging, means that with this algorithm, what you are getting that the distribution that you are looking for is simply the limit distribution for this process, and you are creating the empirical distribution based on that. Means you need to cut the first part of the Markov chain, and even this distribution, because this is based on this, that you are doing step by step, is quite strongly correlated for some small shifts, which means that in fact this is very slowly converging and very low effective. And then the problem is that if this model is based on something what is very simply computable, you can do this approach, because to get something reasonable, you need to make like 100,000 of steps of Markov chain. But if you have a model which is more complex and the computational cost for computing this, to evaluate this, is quite high, simply it doesn't work. And this is the reason that people were going to the different methods. And the now quite popular approach, which is now we are coming from something what is to really to mathematics, is the approach which is called the gradient flow approach. This is the methodology. You know probably very well from the analysis the method of gradient method. Means that for the real function, for example, minimalization of the real function by the gradient method, which means that you are all the time going down to the gradient, and if you have a convex functional, then you can, based on that, you can get to the point which is a minimum. And this is a similar approach, but now we are trying to minimalize not the functional which is based on the okay, this is a functional which is on Rn, but functional on the probability measures. And then the probability measure, as you know, is unfortunately not a linear space. And then the definition of the gradient is slightly tricky. And there are two possibilities. One is that you are considering this metric gradient in the sense of some minimal descent method, because here is the gradient, which is a probability measure, but it's not really the gradient. And another is that in fact, these probability measures with the so-called Wasserstein distance, this is Riemannian manifold, and you have also some Riemannian structure for that. But I will not really go to this point because this is too complicated. Particularly, it's definitively not enough 2 years of the mathematics to understand what is behind.
Sorry, may I have a question?
What? Yes.
May I have a question here? So this equation is the Fokker-Planck, or?
Okay. On the next slide, there will be really the Fokker-Planck. If you, I will say in which situation it will be the Fokker-Planck.
Okay, thank you.
And then this is if you want to, the first paper probably is not so good, but there are several papers like probably quite good is the Cedric Villani book, Optimal Transport Old and New, and also very nice this Sant'Ambrogio. Particularly, this is written optimal transfer for applied mathematicians. But here the applied mathematicians are more like people PDE than people really apply it, like just doing statistics. But still, there is quite a lot of applications, and just to have some monographs and now to explain you what is the strategy, because this is important from real life to know what is the strategy, how you are doing, applying this gradient method. The strategy is exactly like you are in mountains, you are outside slopes, and for example, here there is no fog, but imagine you are in fog. Here, this is in fact in Dolomites. This is one pass in Dolomites. Quite nice, but first part was difficult, I will say, quite slopey. And in this case, the methodology is very simple. Means if you want to get down, then you try to find you make around you some circle, and you trying to find the point in the circle with the smallest possible altitude, yes? And then if you follow this methodology and you hope that there is a convex and there are no local minima, then finally you go safely down. There is, of course, another assumption which is important if you are applying this methodology in practical life. The assumption is that there is no, the functional is enough regular and there is no gradient catastrophe. It means there is no rocks that you will ski and then there is like 50 meters and life is generally risky. You should be careful, but if there is enough functional is enough regular and you hope on some convexity and that there are no local unconvex parts, then you will go safely home independent of the fog in the mountains. And here is, this is as usual, we need, like sellers, we should give you that the method is the best one and perfect one. You can read like the advertisement for the gradient method. But let's go to, because there was a question about the Fokker-Planck, and this is very relevant question. Before we will get the slide with the Fokker-Planck, in statistics, quite important measure is the Kullback-Leibler divergence. I will not say distance because you know it doesn't satisfy the triangle inequality, not really the distance. But this is in the for the distributions you have this form, and this is some measure which is very relevant for the, for example, for measuring how one distribution is far from another.
So your space is finite. This x,
What?
this curly x is finite. The countable.
Countable. In this case, if I have index, but in fact, then later on I will go for the distribution. You know, this is inconsistent, in fact, with what I will say later on. I'm saying some typically, you know, for countable index, you know, you have this type of the expression, because if you will have a sum over something what is non-countable, and it will be, you know, strictly positive, then of course the sum will be plus infinity. Then the index needs to be, as usual for sums, needs to be countable. But this is not really what I will go later on, because I will go for the continuous situation with the continuous distribution and not for the atoms like it is written here. This is more like, you know, the statisticians are quite frequently using this for atoms, but I will go for the continuous counterpart. And now we have a Fokker-Planck. And the Fokker-Planck is exactly this equation. And, you know, you have a divergence, which is simply the derivative, which is you have a matrix, and you take a trace of this matrix, and you have a gradients. The gradients are like in analysis course, and you have a time derivative, you have a space derivatives, both divergence and gradient are only in space. And the observation is that if you take such an equation in full space, means, for example, on Rn, then you can ask, what is the limit or the stationary distribution or the stationary solution or the long time limit to this equation? And this is simple computation, what you can do, that if you want this to be stationary in time, then means this time derivative should be 0. And if the time derivative is 0, let's assume we can skip the divergence, if you know, and then we can say, okay, the stationary distribution is just solving this equation.
But sorry, am I right by saying that if this potential V is 0, you get a heat equation?
If the potential V is 0, you get a heat equation.
Constant even.
There is a problem. The constant is not a probability, constant 0 in some sense.
Everything should be integrable, yes?
Yes, because this equation is a conservative, means this equation is conserving. If you have non-negative solution, then automatically, because here is the divergence, and immediately from the Stokes formula, you know that the integral of rho is conserved in time. If you have a constant solution and you start with the finite mass solution, it's somehow contradicting. What is going for pure heat equation is that simply the equation is vanishing everywhere, and the solution is spread on the bigger and bigger, converging everywhere to 0. The mass is still constant, but solution is escaping to, I will say, plus infinity. The role of this potential is extremely important, because this role of the potential is somehow keeping the mass in giving possibility for some steady distribution of this form. Because if you have here the 0 potential, then somehow is coming nothing. Everything is spreading. The mass is simply spreading.
Okay, and the last question, how do we think about the zero in the physical context? Is like a density of particles, or?
Particles is difficult to say because this is a equation. The question is, there are some, if you are talking about the rigid particles, means the sum of the delta Dirac, unfortunately, this evolution of this equation is not preserving. It will be later in my talk. This is the difficulty is not preserving the rigid particles. Means that there is immediately spread of the. If you start with the initial data in the form of delta Dirac, immediately you are getting the distribution, which is of course continuous.
Okay, I see.
Back to Lebesgue measure, but this is unfortunately this is exactly the problem. Unfortunately, the life is not so easy. But what we can think is there is a physical interpretation that you have a particle and you have some field. And on the stochastic level, which will be on the next slides, on the level of Langevin equation, what you will get that in fact this evolution, you have a Brownian motion of the particles. And then additionally, you have some force which is trying to keep some potential which is keeping the particles in some area. If the potential is convex, then you can hope on the situation that you will get some stationary distribution. And because solution, because this equation is a conservative one, if you will start with the solution which has a mass 1, it will remain forever. Means finally you will get with this, if you start with something what has a mass 1, you take a proper potential, then your limit distribution is exactly what you are looking for the Bayesian inverse problem.
Okay, but still, okay, so maybe it is not right to think about the zero as a density of number of particles, but still like a density of a mass. Is
yes,
it correct?
Exactly. Density of the mass of the distribution, evolution of the density of the mass of the.
Okay, thank you.
Now you are not looking this. You don't need to look for this normalization constant, because in the evolution, if you start with 1, you will always remain constant 1, means there will be exactly proper normalization constant for the limit. And this is a Fokker-Planck, as it was mentioned, this is a Fokker-Planck equation, evolution of Fokker-Planck equation. And what is known still, I think in 90s, it was discovered in 90s on the level of the Fokker-Planck. There was Markovich and some other mathematician. They discovered that if you take something what is called relative entropy, particular case of the relative entropy, this is Kullback-Leibler. If you take a function S log S, then you are getting exactly the Kullback-Leibler for the continuous distribution. Then if you take a relative entropy, then there is a simple trick that you can, in fact, explain on one slide, just saying you that this relative entropy between the distribution that, or Kullback-Leibler divergence between the distribution that you are looking for and the evolution of the process is just going down. This is because this term, it is easy to this is a several line of the computation from the equation. If you assume that you have enough regular solution to get this line, and after that, this is a simple argument that this is always negative, because this is a second power here is a minus. And this is 0 only if these two guys are simply proportional, because this is only the situation that this gradient is 0, which means that the relative entropy is between the stationary solution that you are looking for and your evolution of the process is decaying up to the moment that they are proportional. But because your normalization constant is the proper one, means this is a proper, all the time this is a probability distribution, this rho t, for all t this is a the probability distribution, then finally you are getting exactly what you want to get. And this is the, if you want to get, there is also the method to get, this is something what is more, you know, tricky. This is so-called Loxobolev inequality. And with the help of the Loxobolev inequality, you can even get the exponential decay of the Kullback-Leibler divergence. And this is like observation from PD from 90s. And in some sense, in similar, even I think it was 92, but at the same time, there was people for this were using the, you know, Fokker-Planck. This is a deterministic equation for the density, for the evolution of the density distribution for this stochastic equation. And on the level of this stochastic equation, there was a paper of Robert and Swedy, and they find, oh, sorry. They find following.
So excuse me. So the distribution of xt has density rho.
Exactly, Fokker-Planck.
Okay. Okay.
There's we have stochastic process and we have equation for the distribution of the density for each time for this. And this is the from the point of the stochastic PD. There was a paper of this Robert and Tweddy. There was one. There is also they were using, in fact, to prove the convergence. They were using argumentation from, as far as I remember, argumentation from the some asymptotic argumentation based on some asymptotic properties of the Markov processes, and not really this close to the slightly different argumentation. But later on, there is a paper of Błażej Miasojedov with his with some collaborators, and they were proving exactly in the frame of this Kullback-Leibler distance and in the context of Wasserstein distance, which is also here. Okay, and now there was some idea, and you know, this is quite frequently we have some nice idea which are really powerful, and we're trying to find why they doesn't work. The idea was just to look on the Fokker-Planck and as an equation for the rigid particles. Means to start with some rigid particles. That was what you were saying. Oh, this is the evolution of the particles. And try to use maybe not Fokker-Planck, but maybe this JKO scheme, or some people are calling this minimalization movement scheme, means that scheme which is exactly what I was saying about. You look around 20 meters and you find the point with the minimal altitude. This is exactly the minimalization scheme, or the JKO scheme in the case of the real application to skiing. And to try to apply this directly. But there is a problem. The problem is, if you want to look for the Fokker-Planck as a gradient flow with respect to Wasserstein distance, then this is a gradient flow of this functional. This is somehow surprising, but the problem is that you need to write in very particular form this Laplace part. In fact, this is, you are doing something what looks to be crazy. I will use the sorry for only for people here. If you have Laplacian of rho, then you want to write Laplacian as a divergence, and now you know you are doing something completely crazy. Means you are writing gradient of log rho times rho. And now what you see as you are applying this gradient, then you are getting gradient rho times 1 over rho, and you can cancel this, and this is exactly Laplacian. And unfortunately, passing to the Wasserstein distance, the cost that you are passing is that you are doing such a crazy tricks. And because of that, finally, the functional that you are trying to apply the gradient is not something very nice, but you have this term. This is exactly the term coming from the Laplacian of rho. And now you want to apply the delta Diracs to this. And unfortunately, you cannot, because to apply these all schemes, you need to start from the domain of the functional. And what you can observe is that if you want to put here the delta Dirac, you cannot, because here is log of density, and delta Dirac has no density. Okay, let's try to, for example, to use some modifier and put some like a to minus and concentrate it. And then you will see that if you want to somehow approximate the delta by some continuous distribution, and you are trying to put this and you pass to the limit to really to get to the delta, then your functional is exploding to plus infinity. And it makes the problem for the convergence of such an algorithm, and you can simply not converge in such algorithm. You cannot use the initially some constellation of delta Dirac and apply nicely this Wasserstein distance. Nevertheless, this is a distance which is defined for quite arbitrary probability measure. The functional, which is for the Fokker-Planck, is only defined for well-defined for the probability measure, which are such that this is, this is simply integrable. And this is a constraint and you cannot pass by. And this is the problem to apply this method, so-called deterministic method for sampling. But people get some idea. The people were getting this idea in that sense that people were just, for example, just switching to slightly different equation with the same limit distribution. Because in fact, we don't care about Fokker-Planck. We care only about the limit distribution which we are looking for. What is the equation which is giving us the evolution of something what is converging to this limit distribution, in fact, doesn't matter. And the one is so-called Stein variational gradient descent method. In fact, it was just, this idea was written in not completely clear way in some journal or on some conference for the machine learning. But if you go exactly mathematically what is inside, then you are beside of this minimalization scheme which is written there, you have this equation. Here the difference is that there is a kernel which is regularizing, and because of that now the delta Dirac and the distribution is not the problem. And now you can solve this PDE, which is difficult to solve, and you need by some simple system of ODE, because there is you can easily, there's something what is called mean field limit. You can easily prove that if you take enough big amount of such particles, then you will get exactly the solution to, and this is exactly the method to make now the sampling deterministic and no longer based on some stochastic equation, which is somehow, in some contexts, it's better simply. And this is the story is quite, the idea, original idea is, as you see, quite new. The number of citation is all the time quite rapidly growing. But this is like, I think 1 year ago, okay, maybe not one, that probably the time that I was just on this interview, there was this time of the citation. And in fact, there was some try to prove that this method, because there's one thing is that the algorithm is working, as we know, and another, this is the testing, and another is verification. And for verification, you need the mathematics, really. And in fact, the first verification of this algorithm, really verification, that these two papers are also bringing quite close to the verification. But the first full verification is from the paper of Jose Antonio Carrillo and Kuba Skrzydkowski, both from the University of Oxford. In fact, Jose is from Queen's College. Kuba is now from the beginning of new academic. He was a postdoc of Jose in Queen's College, and now he is in St. John College in Oxford. And Kuba was my PhD student. This is the reason why I know quite well the development. And this is in fact the method, also the method that they were applied here was in fact based on the method which was developed in our monograph with Kuba, Ania Marciniak-Czochra from Heidelberg. She's professor in Heidelberg of mathematics, and Christian Duhl, who was a student of Ania at this time. And I think my time is over, and it's good time to stop. What? This about the so slowly growing.
Okay, are there any questions or comments, please? And people on Zoom, are there any questions? Okay, maybe we are talking about this weather forecast. Is there a relation? Maybe can you say something? Now I will understand more than yesterday.
Yes, at our discussion during the dinner.
Since we have time, maybe you can say something.
Yes, maybe that's good, because there is I will say maybe one sentence that my impression is that first there is some message before I will go shortly to weather forecast. The message to take home is that around us there is a lot of interesting mathematical problem based on deep mathematical theory. And this is quite important to be open-minded for reality which is surrounding us, not only to sit in your office, and or in your room and think about some small part of the mathematics. And coming back to weather forecast, yes, there is several. Means first the weather forecast and the calibration of some parameters. There is a question of the methodology for calibration of the parameters for the weather forecast, because this equation, as usual, like if we are mathematician, then if we have equation, then always equation with all constant one, because this is the simplest, and we say that's good. But in physics, in real life, there is important some parameters. Some of them are small, some of them are big. And sometimes there is also, based on that, we can say, some terms are negligible in there. And what is important is that for these weather forecast models, what we are doing in ECM now is only one forecast. It means we are doing this data assimilation, creating the initial value, putting the information that we are getting, we are creating one scenario of the weather forecast. The plan for future, which we discuss with the director for the weather forecast in ICM, and there is some team working there. There's Karolina Szafranek, and there is a Dr. Marta Kopeć, who is the physicist from also originating from the Warsaw University, but from the atmospheric physics. She was a PhD student of Malinowski. And the idea is that what we are doing now is I will say one shoot of the weather forecast. But the problem is that the weather forecast is sometimes quite unstable with respect to small perturbation of the initial data. The initial data that we are getting due to the assimilation and also some inputs are not exact, but somehow perturbed. Then what one should go is to should at least try to represent some empirical, I will say, empirical distribution. Means that not that like here you see that there is one line, but some and with some margins which are added, in fact, with quite artificial way, but just to start with some amount of simulation based on some proper perturbation of the initial data. For example, based on some distribution that we are assuming distribution of the initial data, and then try to conduct some information which is more about the probability, temperature. You have some diagram of like with certain probabilities in this range, in certain with this range, and this is in fact the newest papers of Edristiti are also going on, giving some mathematical background for this. He's doing on the level of the two-dimensional Navier-Stokes equation some Bayesian inverse problem for the initial data, which means that he is somehow, because this is and this is also the direction that we want to this weather forecast weather forecast team wants to go. But this is of course difficult, and then this is a question of the proper computer power to make this. And this is also theoretically there's a lot of theoretical problem to solve to find the proper way for this. But this is really strongly connected for the fact that here this is in fact you have not exact initial data, but up to some perturbation, and you should also at least make some amount of scenario which will show that okay, temperature can be in some range, and but this is a question not to how to combine the theory and the practice in the computations, which is not I'm not promising you that the next year you will get the weather forecast, our weather forecast, which will involve this. This is more like several year project that we want to go.
Well, but weather forecasts by ICM are great. I check them a few times a day, and usually they are. When I say to my husband, okay, it will be raining at 10 o'clock, it rains at 10 o'clock. So
I'm very happy. I will say to our
pardon. Well, maybe.
There is also I would say for you young people also this is quite important, quite possibility. If someone wants to join our team in ICM, there's also the possibility, because there's one part is of course the coding of and working on the model, Another, we are trying now for also applying for some. This is not, I think, not very secret. I should say, applying for some grant to Foundation for Polish Science to big some, and the grant idea is together with the Institute of Oceanology of Polish Academy of Science, and this is more on the model of to put together the model of waves on the sea and the flow of the water on sea together with the weather forecast. Nevertheless, if someone wants to go on the border of applied mathematics and to join the team of ICM, please contact me, because that's we are trying to for some development you need young people, open-minded people, and you need some group simply. Like Eva was saying, that one single person is not able to make any real development, and we are really in fact, I was employed by rector of Warsaw University. One of the reasons was this, to just to make some more in the science direction in the ICM.
Okay, please.
So I'm hesitating to ask these questions, since I'm afraid that this could be too broad and too general, but nevertheless, let me try. So this Fokker-Planck equation is something which is on the level of being macroscopic, yes, since you are dealing with a density of a mass. Mm-hmm. Okay, you can go, forget quantum stuff, and you can go to the microscopic level where you trace every trajectory of a particle, treating it like a solid billiard ball. Mm-hmm. So this is one level which I would call microscopic. Mm-hmm. But and now, please correct me if I'm wrong, that there is also some kind of intermediate level, like a mesoscopic, mm-hmm. where you treat your particles as point particles, like mm-hmm. like a solid balls, mm-hmm. But you really trace the behavior of the density of the number of particles. And correct me if I'm wrong. So is it related to the so-called Boltzmann equation?
You know, there are, as you are saying, generally in physics, you have three levels, so-called microscopic for like Newton dynamics. Yeah. You have a mesoscopic level, which is Boltzmann or Warsaw equation. And
Boltzmann or, sorry?
Warsaw. There is a, depending. And that on the microscopic, you have simple particles, and you have, like, for example, in physics, Newton interaction between mm-hmm. the simple particles. Mm-hmm. On the Boltzmann or of Warsaw level, you have a distribution of the particle, which is on the space time. Okay, in fact, distribution, then it means space and velocity.
Phase space, yes?
Yes, that you have, still you are keeping, you are trying to be more macroscopic, but still you are leaving the velocity distribution of the velocity in each point. Means that what it means physically that you try to build something what is macroscopic, but still you see that the particle in one point are somehow flowing in the different directions. And of course, you have a last level, which is Euler equation or Navier-Stokes equation, which is fully macroscopic. Here, in fact, if we are talking about the Fokker-Planck on this level, then Fokker-Planck is you know, this typical way that you are talking is more for the second order models. What means second order models means that you have a position, velocity, and acceleration, like in Newton dynamic. Fokker-Planck is more the result of the so-called, I think it was Euclides dynamic, which was saying that the velocity is proportional to force. In Newton dynamic, velocity is proportional to the acceleration. And if you go like Boltzmann, Then you start from the second order model, means the Newton dynamic, and you are getting to Boltzmann. You have linear transport plus bilinear collision term on the right hand side, which is just saying you how the particles are colliding, and then at the limit you are getting the typically Navier-Stokes or Euler equation as a result of this. You can also pass from Navier-Stokes or Euler to the Fokker-Planck, but it needs also some additional scaling, which are not very typical. And you can bypass, because there's a typical are, for example, high pressure, so-called high friction limit for the which allow you to pass from the Euler equation to the porous media equation, like, or this type of the equations. But this is to build this middle stage mesoscopic level for this type of the equation is slightly more tricky, because this is based in fact on the idea of the first order dynamic. Velocity is proportional to the force, and not velocity is proportional to acceleration.
Oh, I see.
This is a longer discussion this is also this is quite important as we are, as mathematician, we are going to discuss with people like, for example, from physics, that simply is this is then difficult, because in fact physicists, they have quite nice background for but they are also very specialized, I will say that.
Do we have time for a follow-up question? Could I ask another? But since I know that...
Maybe let's stop, because we want to make
a photo, yes.
Photo, and you can just...
yes, I will answer this in private communication.
Okay, so let me just stop recording.
Thank you very much for invitation once more. Okay.